Okay, so I want to discuss a topic today which involves the probabilities. Okay, so quantum mechanics is intrinsically an indeterministic theory. So we have these superposition of states, and when we make a measurement, we obtain a probabilistic result, okay, in which the probabilities are proportional to the magnitude squares of these expansion coefficients, okay, involved in the superposition. But we also have, of course, a classical probabilistic description of nature. Certain things are not deterministic, independent of quantum mechanics, and we have probabilities associated with them. So let's discuss an experiment that will perhaps clarify things a little bit. Suppose I am making an SZ measurement of spins coming in, okay, electron spins coming into an experiment. And I know that there are two possibilities, okay, so there's going to be plus h bar over 2, okay, that is something that we call the up z state. So I know that electrons going out over here are in the up z state, okay, or they can be in the minus h bar over 2 down z state, okay. So now what I'm going to do is I'm going to randomly, okay, by classical random process, I'm going to send either these particles, okay, or the other ones into the next experiment, which is going to measure the x component of the spin, okay. So, okay, sometimes I'll send these spins there, sometimes I'll send those ones there, okay. Now, as long as I am measuring up spin or down spin states, okay, it doesn't matter. The probability of getting up and down here are going to be the same, right? Because I know that this up z state may be written as 1 over square root of 2, okay, up x plus down x, right? So the coefficient for expansion is 1/2, so I'm going to get 1/2, okay, of the particles going in the plus x, okay, so this is going to be plus h bar over 2 measurement, that's going to minus h bar over 2 measurement. But overall, I'm going to get a 50-50 distribution because, okay, I'm either measuring an up z or a down z, and they are going to give me a balanced measurement over here. So the measurement of Sx, no matter what I do, whether I choose these particles or those particles, they are going to be the same. On the average, this person making the measurement is going to get 0 average. But if I do something like this, suppose I send in particles which are in a quantum superposition of 1 over root 2, okay, up z and down z, okay. So this is a case, okay, so this is a case in which I am sending in these particles in a superposition of up z and down z, okay. Now, if I try to make a measurement, I'm going to get 50% probability of getting an up z or a down z. But if I just send this over and make an Sx measurement, okay, what am I going to get? This is actually an expansion of the up x state. So I'll definitely, okay, get plus h bar over 2 here. Okay, so in this case, the Sx, okay, average is going to be plus h bar over 2, and it will be definite. Okay, so now you see over here I have up z and down z with 50-50% probability, but it's a quantum mechanical probability. Okay, it's a superposition state. Whereas over here, I am putting in 50% of this or 50% of that, but it's a classical probability. So this object measures either this state or that state instead of measuring the superposition. Okay? So I have these two types of probabilities, and there's a mechanism which keeps track of these two types of probabilities very elegantly. Okay? And it's called the density matrix formalism. Okay, so let's just look at what that is. Okay, we define the density matrix. Okay, so matrix in this sense means just operator. Okay, so we define an operator and we call it rho. Okay, so this is defined as, okay, a sum over the states which are possible for the particle to be in. For example, over there, we had 50% up z and 50% down z, right? So the states that the particle can be in are up z or down z. But let's keep it general, okay? So suppose the particle can be in one of these states, psi n, and I'm going to write it like this, so it's opposite of inner product, okay? And multiplied by Pn. Okay, so what is this? Okay, so, well, I should sum over n. Okay, I sum over n over all the states that a system can be in. Now, these states need not be orthogonal, okay? So these states, okay, not necessarily, okay, orthogonal, okay, but they are all normalized. Okay, so all psi n are equal to 1. Okay, so they are not necessarily orthogonal. Obviously, that also means not necessarily complete. So just a bunch of states, psi n, in which the state system can be in. Okay, so for example, I may be, again, suppose I'm doing this Sx measurement that I used in my example over there, and I'm going to measure what the result is, and there's something coming in. Okay, I don't know what the incoming state is, but perhaps it will be given to me that, well, it can be an up z state, just like we had over there. It can be perhaps an down x state, okay? Possibly, okay, and I don't know, an up y state with certain probabilities. So probability of this is perhaps 1/2, probability of this is 1/4. Okay, so this has to be 1/4. Okay, so someone tells me that there's this collection, okay, of particles that are coming in with these probabilities. So you see, these are not necessarily, okay, they are not in fact orthogonal to one another, okay? But I am assuming that there's this collection of particles in various states coming in with certain classical probabilities. Okay, so these probabilities here are just the classical probabilities, okay, associated with each one of these states. So Pn are the probabilities. Okay, so these are the classical probabilities. Okay, so what do I do with this operator? Okay, so this is now an operator. So why is it an operator? Because if it operates on something, it will just hit it with this bra vector and will give you a ket. Okay, so a ket will be transformed into some other ket. Okay, so that's how we looked at the matrix representation of operators, and that's our definition in that sense. Okay, so let's look at some properties. Okay, one thing that we are going to first look at is going to be the trace. Okay, so trace of rho. Okay, what do I mean by trace of an operator? I go to a certain set of complete states, and I look at the diagonal elements. Okay, so I take any set, rho, I like this, I, okay, and I sum this over all possible states. Okay, so let me just emphasize that. Okay, so this is actually any complete, okay, orthonormal, okay, set of states. So what does this give me? This gives me the matrix element of rho, but it's the diagonal matrix element. Okay, so this whole thing here are the diagonal okay, matrix elements of rho, okay, some terminology in the representation of states I. Okay, so obviously if I choose a different set of values, a different set of orthonormal sets, I am going to get a different set of diagonal elements, right? It just depends on what I am using here for these sets. But we have an interesting theorem. Let's just go over that. Let me, okay, do it over here. So let me just look at what I can do with trace of rho. Okay, so if I take trace of rho, let me just write down exactly the same thing. I, rho, I. Okay. And now suppose I choose a different set of, well, let me do it this way. Let me just put in a set of identity operators here between rho and I and between this rho and I. Okay, so the first set of identity operators that I'm going to put in is going to be a set of complete states. Remember how we put in orthogonal, so I have to use a different index, J, J, J. Okay, so now I go to a different basis, a different set of orthonormal states, okay, and insert an identity over here. And I'm going to insert another identity here using the same states, but now I have to use a different index, AK, AK. Okay? So what happens? This is now equal to a sum I, J, K. Okay, so where are we? I, A, K, A, K, right? Row, A, J, A, J. Okay, and then A, J, and I, right? Okay, did I get everything right? I just put in two states, okay, which are just identity operators. But now you see I have this I and I, which can be combined together. Okay, so let me just rewrite this. Okay, so that let me move this. Remember, this is just a constant now. It's an inner product. So this is going to be I, J, K, A, J, I, A, K, and then A, K, row, A, J. Okay, and here I have an identity operator along with I. Okay, so I can just remove that. So that all reference to the original states are gone. And once I remove that, you see I'm going to get an AJ. So this is going to give me AJ, let's see, I made a mistake. This was AK, right? Okay, because this was identity. So AJ, AK, which means that this is going to give me a delta JK. Very nice. So if I now sum over J, wherever I see a J, I have to put in a K. So that gives me very nicely AK row AK. Okay. Okay. So you see this is still the trace operation, but with an arbitrary different set of orthonormal, okay, functions. So that means, what that implies is that the trace operation, okay, is independent. In fact, the trace result itself is independent of the basis, okay, used for the inner product. So I started with I introduced an arbitrary set of orthonormal states, and that means, and I got the same thing, which means that this is independent. So this is very nice. This trace operation is independent of what type of functions that you use. Now, that means if I, in general, if I use, okay, so if I am finding the trace of any operator, A, okay, so what I can do is, since I am free to choose any, okay, function, any complete set of states I like, what I can do is I can use the eigenstates of A, okay, in this expansion. If I use the eigenstates, okay, so if I have a choice, so if I use the eigenstates of A, okay, then it's going to give me, okay, what is A times AK is going to be the eigenvalue, right? So this is going to be, let's call it lambda K. So it's going to be some K, AK, AK, lambda K. And these are 1, so this is going to give me some of the eigenvalues. So this now says that the trace of any operator is equal to the sum of its eigenvalues, okay? All right, so let's see what trace of rho is going to give us. Trace of rho is going to be, okay, let me just rewrite what we already had. Let me choose an arbitrary set of states, and then for rho, I'm going to get these psi n's, right, and psi n's, and the probability. Okay, so remember that rho is this Pn, psi n, psi n, and I just am going to put it in like this, okay? Now, you see I have a sum over I here, and I have the I index there, so let me again bring those things in together. So I'm going to get what I n again. Let me put the Pn to start. Psi n I psi n. Okay, but now I'm summing over I, and these i's are next to one another, and that means that's going to give me an identity. So that gives me sum over n, okay, Pn psi n psi n, but we said these were normalized, so these are all 1. So this is the sum of all probabilities, which gives me 1. Okay, so the long story short, trace of rho is always 1. Okay. All right, now why would this be a useful object? Let's look at something like this. Let me take the trace, okay, of rho times any operator. Okay, so I take trace of any operator. So what does that give me? That gives me a sum, okay, again there will be 2 summations. One because I am taking the trace, so I'll need these complete set of states. So let me put them over here, I, and there will be another one over here, I. Okay, then there's rho. Rho is just Pn. So let me pull the Pn out. Pn psi n, okay, psi n. So that's the rho part. And then I have this operator A. Okay. So again, there are actually very few new ideas in this. You see there's an I there and an I there. So I can arrange things so that I can get an identity. So I'm going to get In. Let me move this In to the back. It's going to be psi n A I psi n, okay, Pn. And I use this I and these i's together, which will give me an identity. So I can take that out. So that will give me sum over n psi n A psi n, okay, times Pn. Okay, now you see this is actually quite an interesting and useful result. Why? Because this is, okay, this term here is the expectation value of A in any one of these states. Remember, again, where we are coming from. So these are the states, okay, psi 1, psi 2, psi 3, whatever. Those are the states that the system can be in. So this is the expectation value, okay, of the operator A for each one of these states. So some A will have some expectation value for psi 1, some expectation value for psi2, etc. So this is now the quantum mechanical average. So it takes care of the quantum mechanics part. Whatever the probabilistic events here are, okay, are taken care of in this expectation value. Okay, so this is the quantum mechanical average, okay, of A in state psi n. I find that, and then I multiply that by the probability of that state occurring, okay, the classical probability, and take a classical statistical average, okay? So together, okay, with all of this is the statistical, if you like, the classical statistical average, okay, of these psi n, a psi n's, okay? So with some probability p1, I am going to get this a11. With some probability p2, I am going to get a22, and so on, okay? And this just averages that out, okay? So we give this a new notation, okay? We put this in brackets like this, okay? So this thing we call the ensemble average.
So it says average of averages.
Yes, ensemble average. Ensemble means a collection. Okay, so here we have a collection of states. So this is our ensemble. Okay, these probabilities define our ensemble. And we have an ensemble average of operator A when I have a quantum mechanical system in which I have various classical possibilities. Okay? So, an example of such a situation were the thermal averages that we were using. Okay, so when we are calculating, okay, when we are calculating the averages, okay, so when we look at these thermal averages, go to another pen. What did we do? Okay, we went through a process in which we said, okay, let's just maximize the entropy, etc., whatever we want to do. But then we said, okay, the system can be in one of these states with some total energy E, okay? So I have a system in which the total energy can be one of these objects, E1, E2, E3, E4, etc. And we said the probability, okay, of this nth state is going to be e to the minus En over kBt. Okay, so this is now a thermal average. It's a, okay, classical probability. I have to normalize this, okay, so this is what I have, Z, okay, some normalization constant. How can I find that Z? Well, sum of all of these things have to be 1, so you can easily see that this Z has to be equal to sum of all of these e to the minus En over kBt's, okay? So if I just sum over these things, I get the normalization constant, okay? But together now, with this definition of Z, I have these classical probabilities. And for thermal averages of any object, okay, we were using, okay, we did not use this notation, but what we were doing was we were just multiplying this Pn, okay, this exponential factor, with whatever quantum mechanical average that we had, okay, so this was something which we can call An, okay, so this is what we were doing. Now, looking at it from a quantum mechanical perspective, the averages that we found were simple things. We found the average of energy, for example, okay? We found average number of particles. Okay, so, but in general, you can have an arbitrary operator there and find its average in a certain state. Okay, so how would I do that? Okay, so each one of these states would correspond to a wave function. Now, in this case, the states will be complete and orthonormal, so our life is going to be a little easier. Let me, in fact, give them a different name. Okay, so let me call them, let's see, E1, small e1, small e2, small e3, small e4. Okay, so I have a full Hamiltonian of the system, which says that H operating on any one of these ENs is equal to these capital ENs times ENs, small e. Okay, so these ENs are eigenstates of this Hamiltonian operator H, okay? And I have something which looks like that. So in general, for a general operator, let me just look at the density matrix and generalize this. Okay, so this is going to be sum over n. There's going to be this e to the minus en over kbt, okay, divided by z with the proper normalization. And then the expectation value, quantum expectation value of my state in the nth state, right? So this is going to be the average value of this operator in the nth state, and that will be its probability. Okay, so there are two probabilities here, two types of probabilities. One of them is hidden inside this expectation value. That's the quantum mechanical, okay, quantum mechanical average. And then I have something which does something like that, okay? Now, one thing that I can do to make this look a little bit more elegant is to notice that this En is an eigenvalue, okay? It's eigenvalue of the Hamiltonian. So I can write this, okay, as the trace. Okay, let me first write it, and then we'll discuss what I have written. Trace of e to the minus the Hamiltonian over kbt, okay, times a. I still have the 1 over z. Okay. Why is that so? Well, if I take the trace, let me take the trace over these ENs. Okay, so this is going to be, let me put a question mark here. Okay, I have just written that down, but let's demonstrating that that's true is very easy. Okay, so what do I get if I evaluate the trace of that? Well, I have to sum this over all possible, okay, states of the of some set of complete states, and I choose them as the eigenfunctions of the Hamiltonian. Okay, so I'm going to have e to the minus h over kb t over z, okay, times a times ei. Okay, but now since this is an eigenfunction of the state, I can just convert this part into I, okay, e to the minus EI over KBT. Okay, operating toward the left, it's a Hermitian operator over Z times EI A EI. Okay, so I get this immediately. Okay, so since that checks out, that means that the density matrix operator for this system is going to be e to the minus h over kbt, okay, divided by z. And z is just going to be the trace, okay, remember what z is. Z is this, just sum of the eigenvalues. Okay, so it's going to be trace of e to the minus h over kbt. Okay, so that's our, those are our two results. Okay, so that's the density matrix for the system, e to the Hamiltonian. So this is exponential of an operator, so you have to evaluate it carefully. Okay, and that's what you get for the okay, and that's what you get for the normalization constant, and that's the thermal average. Okay, so we have been doing this in a sort of abbreviated way. Okay, we just put in e to the minus en, and then over here we just put down the energy. Okay, so if you want the average value of the energy, then it becomes very simple, right? You just put an en here and make the summation, and that was your last homework, right? You summed this over some number of states, some possible number of states that were available to you. Okay, any questions about this? Yes?
In this density formalism, do non-diagonal entries contain any kind of information? Because we always talked about the diagonal ones.
Okay, that's an interesting question. Do the non-diagonal elements contain any information? Well, the non-diagonal elements are usually a problem. Okay, sometimes you want to calculate the density matrix, you reduce it from a more complicated one to a simpler one, and then when you do this, you get these off-diagonal elements, and then you have to interpret them somehow properly. It's usually not as straightforward an interpretation as this, but you can ignore them. You can say, okay, let me approximate that there are no off-diagonal elements, or I can just give some physical meaning. It depends on the problem, okay? But that's something important. Okay. And also one thing that you may notice is, well, just to give you some excitement about this thing, you see the way we have also in quantum mechanics something which looks like e to the minus I h bar, well, t over h bar, right, times h, which is an operator for the time dependence in quantum mechanics. And here we have something which looks very much like that. So it looks like temperature is associated with imaginary time and such things. So whether this is accidental or there is some deep meaning in it is for you young people to solve, okay, in the future. But this is just the fact that these are mathematically similar gives you the opportunity to use certain mathematical tools that are available in quantum mechanics to be applied to statistical mechanics and vice versa. Okay, but that's just the mathematics. Whether there's a deeper meaning, whether there's another dimension in temperature, etc., which is imaginary time, okay, those types of speculative things, okay, again, are some interesting problems. All right, let's perhaps do an example so that things will. Okay, we have 10 more minutes. Okay, so let's take an example Perhaps we'll do something like this. Okay, let's take this, okay? So I don't know how practical it will be because I sort of wrote them in random. But suppose we, okay, suppose actually we do carry this experiment out, okay? So I have an ensemble of particles, okay, a random ensemble of particles coming into my experiment, and I want to measure, okay, what Sx average is, okay? So first I construct the density matrix. So rho is going to be equal to sum over, okay, these, I don't have to write summation, I'll write each one of these terms one by one. Okay, so probability of the first event, okay, so that's going to be 1/2. Okay, please check my arithmetic, right? Up z, so it's going to be up z, up z. Okay, that's the first term. The second object is going to be equal to, is going to have probability 1/4 and is down x. So I'm going to get down x, and 1/4, okay, up y, up y. Okay, so since we are going to take the actual trace and everything, let's just put them in the, let's write them in matrix notation in the up z basis, okay, up down z basis. So what do I get? I get 1/2, this is a ket vector, 1, 0, right? And up z, okay, the corresponding bra vector is that, plus 1/4, okay, each one of these things have a 1/2, and this one down x is what? 1 minus 1, right? 1 minus 1, 1 minus 1, okay, plus 1/4, up y was what? Okay, again I have 1/2 coming from both of these things, so it's 1/2, and this is 1 minus I, right? Or is it plus I? In any case, this is the adjoint 1I. Okay, so that's our density matrix. It really is a matrix. So this is 1/2. This is going to give me 1, 0, 0, 0, plus 1/8. Okay, 1 minus 1 minus 1, 1, right? Minus 1 times 1. Okay, is plus 1/8, then 1 I minus I 1. Okay, so let's just add this all up. So what do I get here? 1, 1, 8, 1, 8, 1/2. This is the difficult part, right? This is 4/8, 5, 6/8, right? Yes. 6/8, so 3/4, right? And then this one is minus 1, okay. Minus 1 plus I/8. This one is minus 1 minus I, okay, it has to be Hermitian, over 8. And finally, 1/8 plus 1/8 is 1/4. Okay, so one thing to check, the trace is 1, right? I just add these things together, so the trace is equal to 1. So trace of rho is equal to 1, which is nice, okay? Sum of the elements is 1. So now, if I want to find the average value of Sx, all I need to do is find the trace of this thing, 3 over 4 minus 1 plus I over 8, minus 1 minus I over 8, 1 over 4, okay, times Sx, which is what? 0, 1, 1, 1, 1, no, 0, times h bar over 2. Okay. So let's see what that is. So I'm going to get h bar over 2, which I can factor out because we're just going to multiply these elements. And then I am going to need the trace of the diagonal elements. So it's sufficient for me to calculate the diagonal element. So it's going to be minus 1 plus I over 8. Okay. This one. And the 2 element, which is going to be minus 1 minus I over 8. Okay, and something here, something there, which I don't care about. So the trace is going to be, okay, so h bar over 2, okay, minus 1 over 4.
Not surprisingly.
Okay, so it's glad that you are not surprised. Okay, it's good that you are not surprised. So why? Because, okay, this is going to give me 0 on the average. That's going to give me 0 on the average. That is going to give me minus 1 with probability, okay, 1/2 times 1/4. Okay? Oh, just 1/4. Right? Yes, minus h bar over 2 times minus 4. Okay? All right, so this is a really nice, cute, and extremely useful sort of formalism to extract statistical results from an ensemble of a classical ensemble of probabilities, which also involve quantum mechanics. Okay, let's have our break, and then we'll go on.